Hello, welcome to another exciting class on ExamPadi. Today we'll be learning about equilibrium of forces. In this lesson, we will 1. Explain the equilibrium of forces. 2. Distinguish between the following concepts: static and dynamic equilibrium, resultant and equilibrium forces, couples and torques, center of gravity. 3. Describe the concept of the moment of force and the foundational principles for problem solving. 4. Formulate and solve equations involving the equilibrium of forces. Now let's dive into the concept of equilibrium of forces. In physics, the equilibrium of forces refers to a state in which the net force acting on an object is equal to 0. This means that all the forces acting on the object are balanced, and as a result, the object remains at rest or continues to move at a constant velocity. The concept of equilibrium of forces is based on Newton's first law of motion, which states that an object will remain at rest or in uniform motion unless acted upon by an external force. Let's look at the types of equilibrium of forces. There are two main types of equilibrium in physics. 1. Static equilibrium. In static equilibrium, an object is at rest and the sum of the forces acting on it is 0. This means that all the forces are balanced and there is no net force to cause the object to accelerate. An everyday example of static equilibrium is a book sitting on a table. The force of gravity pulling the book downward is balanced by the normal force exerted by the table, keeping the book stationary. 2. Dynamic equilibrium. In dynamic equilibrium, an object is in constant motion, but its velocity remains constant. This means that the net force acting on the object is 0. A common example of dynamic equilibrium is a car moving at a constant speed on a straight, level road. The forward force provided by the engine is balanced by the resistive forces such as air resistance and friction, resulting in a constant velocity. Let's look at resultant and equilibrium forces. The terms resultant force and equilibrium force are important concepts related to equilibrium. The resultant force is a single force that results from combining multiple forces. Its size and direction are determined by adding up the individual forces. When the resultant force is 0, the object is in equilibrium, either at rest or moving at a constant speed because all the forces cancel each other out. Equilibrium force. The equilibrium force counterbalances the resultant force, keeping the object in equilibrium. It matches the resultant force's size but acts in the opposite direction to maintain balance. In the force board experiment, there are two forces, P and Q, acting at a point O. When these forces are in equilibrium, meaning the object doesn't move or rotate, their resultant force is determined by the parallelogram method. This resultant force, labeled as R, has the same magnitude as the combined effect of P and Q, but acts in the opposite direction. A third force, known as the equilibrium force, is required to keep point O in equilibrium. This equilibrium force is equal in magnitude to the resultant R, but acts in the opposite direction, ensuring that the object remains in a state of equilibrium. Couples and torque. Couple is a specific situation involving two equal and opposite forces separated by a distance and it produces pure rotational equilibrium with no effect on translational equilibrium. Torque, on the other hand, is a more general concept and can be due to various forces, whether they form a couple or not. It plays a role in both translational and rotational equilibrium. In the context of equilibrium, the focus is on ensuring that the sum of all torques is zero for rotational equilibrium, and the net force is zero for translational equilibrium. Equilibrium of three forces acting at a point. The three forces that keep a body in equilibrium can be represented in magnitude and direction by the three sides of a triangle, as shown in this diagram. OB represents the force Q in magnitude and direction. OA represents the force P in both magnitude and direction. And CO represents the equilibrium E in magnitude and direction. This triangle shows the vector representation of the three forces acting at O. The principle of the triangle of forces states that if three forces are in equilibrium, they can be represented in both magnitude and direction by the three sides of a triangle taken in order. The resultant of two forces at a right angle. The resultant of two forces at a right angle is given by R square equals AB square plus DB square. Now let's look at the mathematical expression. Resultant of two forces not at a right angle. By trigonometry, for triangle ABC, we have AB square equals BA square plus BD square minus 2AB times BD cos AD. But cos ABD equals 180 minus theta, that is minus cos theta. Therefore, R square equals P square plus Q square plus 2PQ cos theta, where angle BAC, the angle between the forces PQ, equals 180 degree minus angle ADB. Let's look at resultant of two forces at a right angle. The resultant of two forces at a right angle is given by R square equals AB square plus DB square using Pythagoras theorem. Example 1. The two forces of 20 Newton and 40 Newton act at a point and angle between them is 30 degree. Find the resultant force. Solution. By trigonometry for triangle, we have R square equals P square plus Q square plus 2PQ cos theta. R square equals 40 square plus 20 square plus 2 times into bracket 40 times 20 cos 30 degree. R equals square root of 40 square plus 20 square plus 2 into the bracket of 40 times 20 times cos 30 degree. R equals square root of 3385.6. Therefore, R equals 58 Newton. Therefore, the resultant force equals 58 Newton. The direction of the resultant force is obtained using sine rule. Example 2. If a force P of 40 Newton acts in the direction due east, and another force Q of 30 Newton acts in the direction due north, calculate the resultant of these two forces. By Pythagoras theorem, R square equals P square plus Q square. R square equals 40 square plus 30 square. R square equals 2500. R equals square root of 2500. R equals 15 Newton. Also, tan theta equals 30 over 40, and that equals 0.75. That is, theta tan arc equals 36.9 degree. Therefore, resultant is 50 Newton, making 36.9 degree with 4 Newton force. The next is moment of a force. When we turn on a tap, tighten a knot with a spanner, or screw a nail in or out of wood with a screwdriver, we exert a turning force and produce a turning effect about a point along an axis. The turning effect brought about in each case is called moment of a force. Two factors are involved in each case. 1. The magnitude of force applied. 2. The perpendicular distance of its line of action from the axis or pivot in which the effect is felt or exerted. Therefore, the moment of a force about a point or axis is defined as the product of the force and the perpendicular distance of its line of action from the point. Moment equals force times perpendicular distance of the pivot to the line of action of the force. It is a vector quantity and its SI unit is Newton meter. Principle of moments. The principle of moments states that if a body is in equilibrium, then the sum of the clockwise turning moments acting upon it about any point equals the sum of anticlockwise turning moments about the same point. From the diagram displayed, clockwise moment about O is given as F2x2, while the anticlockwise moment is F1x1. Therefore, the sum of the moment is given as F2x2 minus F1x1. If the bar is in equilibrium, F2x2 equals F1x1 equals 0. F2x2 equals F1x1. In the diagram displayed, taking moment about O, F1x1 minus F2x2 plus F3x3 minus F4x4 equals 0. F1x1 plus F3x3 equals F2x2 plus F4x4. Center of gravity. The center of gravity of a body is defined as the point through which its resultant weight acts. Let's look at conditions for equilibrium of non-parallel forces. For the action of parallel coplanar forces, 1. The algebraic sum of the forces acting on the body in any direction must be 0. That is, the sum of upward forces equals the sum of downward forces. 2. The algebraic sum of the moments acting on the body in any direction must be 0. That is, the sum of clockwise moment equals the sum of anticlockwise moment. 3. The total resultant force must be 0. Let's look at for the action of non-parallel coplanar forces. 1. The vector sum of all the forces acting on the body must be 0. That is, summation x equals 0 and summation y equals 0. 2. The algebraic sum of the moments acting on the body in any direction must be 0. That is, the sum of clockwise moments equals sum of anticlockwise moments. 3. The line of action of the forces must meet at a point. Let's look at the following examples. 1. A meter rule is found to balance horizontally at the 48 centimeter mark when a body of mass 60 grams is suspended at 6 centimeter mark. The balance point is found to be 30 centimeter mark. Calculate 1. Mass of the meter rule. 2. Distance of the balance point from the zero end if the body was moved to the 13 centimeter mark. Let's look at the solution. Let the mass of the rule be represented by W. Taking moment about the pivot, 60 into the bracket of 30 minus 6 equals W into the bracket of 48 minus 30. 60 times 24 equals 18W. W equals 60 times 24 divided by 18. W equals 80 grams. 2. Let the distance of the new balance point be x from zero end. Taking moment about the fulcrum, 60 into the bracket of x minus 13 equals 80 into the bracket of 48 minus x. 3 into the bracket of x minus 13 equals 4 into the bracket of 48 minus x. By opening the bracket, 3x minus 39 equals 192 minus 4x. Collecting like terms, 3x plus 4x equals 192 plus 39. 7x equals 231. Dividing both sides by the coefficient of x. X equals 231 divided by 7. X equals 33 centimeter. We have come to the end of this lesson. Attempt the following questions to assess yourself on this lesson. 1. Explain the concepts of equilibrium of forces with real-life illustrations. 2. Differentiate between the following: resultant and equilibrium forces, couple and torques, static and dynamic equilibrium. 3. Describe the moment of a force with examples. 4. 3 forces act on an object: 15 Newton to the north, 10 Newton to the east, and 20 Newton to the south. Calculate the net force acting on the object and its direction. 5. A 50 kg box is placed on a horizontal surface. Calculate the normal force exerted by the surface and the gravitational force acting on the box. Is the box in equilibrium? Thank you for learning about equilibrium of forces with me. See you in our next video. Bye.